Welcome and get comfortable. Tonight we're traveling far beyond stories, myths, or even the idea of old. We're not heading out into space or drifting into dreams. Instead, we're rewinding the clock, stepping back further than you've ever imagined. We're talking before anyone you've ever heard of existed. Before pyramids, before anyone painted on cave walls, before animals with enough bones to flex. We'll journey to an Earth that predates everything familiar, a planet shaped by forces and creatures now long gone, faded into the depths of deep time. This isn't the kind of trip that needs a suitcase, just a quiet place, perhaps a cozy blanket, and a willingness to let time unspool in reverse. While you're listening, pause for a second. Look around at the walls, your furniture, your own hands. All of it barely showed up at the end of this planet's timeline. Your street, your house, every feature of modern life. These things are all brand new, not just recent in human history, but in the big, ancient sweep of geology. If Earth's story was a movie, you and I would have arrived in the very last second. Before us came an endless parade of forms so different, and so far from human, they're hard to imagine. Let's slow everything down. Take it easy. You don't need to remember every technical name or memorize every detail. Just sink in and let the ancient world rise up around you, layer by hidden layer. Don't rush. If any place can be patient, it's Earth, with more ages gone by than we can count. Now, picture this. What if you hit rewind on our planet, not just flipping back centuries or millennia, but cranking back millions of years in seconds? The landscape would rush and whirl past. Forests would vanish like mist. The oceans would shrink, then surge back in. Mountains would dissolve into dirt, then rise again. Cities would flicker out in an instant, traded for ice fields, then barren plains, then nothing at all. Animals would vanish faster than you could blink. Even continents would slide around, twisting and turning like pieces in a melting jigsaw puzzle. And beneath all that surface activity, something even stranger would be happening. The farther back we go, the more unfamiliar life gets. Eventually, it becomes completely strange. First unrecognizable, then almost invisible. The early days had nothing close to people or animals. Life, if you can call it that, started as chemistry, random molecules floating in puddles colliding by chance. Most combinations didn't last, but a few managed to persist, getting better at hanging on every time. Before we reach the age of dinosaurs, mammals, or any ancestor you'd recognize, there's an even bigger question: what actually is life? When we go back this far, the answer gets fuzzy. We tend to think of living things as creatures that breathe, move, and eat. But at the very beginning, none of that applied. Life started out minuscule, so tiny it was practically invisible, even to our sharpest tools. These original forms didn't chase food or think thoughts. They simply copied themselves when they could. Sometimes they failed, and sometimes that failure led to something new. Early Earth for these pioneers was brutally harsh. We're talking a planet where storms raged, volcanoes choked the sky, and acid poured down as rain. Visitors from space, asteroids, slammed into the ground regularly. Yet even in this chaos, a remarkable thing happened. Not a fish or even a complete cell, but a repeating chemical pattern first appeared. Imagine this as the dawn of a story being told without any storyteller, just molecules sticking together, repeating, because physics said they could. That was enough. Eventually, those repeating patterns started crafting basic walls, tiny bubbles separating the inside from the outside. These simple structures would become the world's first cells and open a new chapter for life on Earth. The planet's original residents weren't anything you'd recognize. Not plants, not animals, just ancient bacteria. More accurately, they were prokaryotes, single-celled beings without a nucleus. They thrived in water, devouring whatever chemicals they could find, multiplying quietly and steadily. They didn't build anything or move in packs, they just were. And for over 1 billion years, they had Earth all to themselves. This detail trips people up. For most of the planet's past, there were no eyes, jaws, or minds, just tiny specks in the dark. The world was microscopic, but it was never dull. Those invisible pioneers got busy transforming their home. Some developed a way to soak in sunlight and turn it into food, not by seeing, but by chemical reactions. This trick, photosynthesis, let them harvest light, but it also unleashed a byproduct, oxygen. At first, this was deadly. Oxygen was a toxin to almost all life at the time. So when these sun-eaters began pouring it into the seas and sky, they caused the world's first major die-off. This disaster is known as the Great Oxidation Event. Earth itself began to rust, oceans turning blood red as oxygen met iron. Countless microbes died, never having faced oxygen before. But out of that devastation, something astonishing emerged. New life forms not only survived oxygen, they used it. These cells were the ancestors of every complex living thing today, including us. This leap from simple to complex didn't happen over a weekend. It probably happened only once, and it changed everything. Somewhere around 2 billion years ago, one cell swallowed another, and instead of breaking it down, they joined forces. The swallowed cell became a mitochondrion, nature's first efficient power plant. This marked the birth of eukaryotes, cells with internal compartments, including a nucleus. Every plant, animal or fungus you know, owes its existence to that ancient partnership. One cell inside another, working together, paving the way for everything to come. It wasn't conquest or survival of the strongest. The real breakthrough happened through surprising alliances. When cells developed the ability to cooperate, everything started to shift. Suddenly, life wasn't just about single-celled stragglers. Groups of cells began gathering together, forming early colonies. To start with, these teams were pretty basic, just clusters of similar cells with no real structure or nervous system. Still, over the ages, some cells began to take on specific roles. Some focused on movement, others on getting energy, a few set aside for reproduction. This division of labor marked the rise of multi-celled organisms, paving the way for life's first experiments with animal forms. But these early animals were nothing like anything we recognize. Most were soft-bodied and fragile, gliding through their world so quietly that many left behind no trace at all. A few, like the mysterious frond-like Ediacaran forms, managed to imprint themselves in ancient rock and baffle scientists to this day. These creatures don't fit well into our family tree. Some had no mouth, no stomach, not even a recognizable left or right side. How they survived and why they vanished still puzzles science, but their existence opened the doors for what would come next. Roughly 541 million years ago, a spectacular turn occurred. An eruption of wild innovation reshaped Earth's biosphere. This flourishing chapter is called the Cambrian Explosion. Despite the dramatic name, it wasn't a burst in the normal sense, but an extraordinary acceleration. New body shapes appeared, new life strategies flourished, and a sudden diversity of species evolved. Many of the major animal groups that exist today trace their roots back to this window of time. Creatures like primitive arthropods, early mollusks, bristled worms, and bizarre spiny swimmers with no modern descendants filled the seas. Predators and prey now took center stage. The first eyes appeared, capturing light for the first time. Shells and armor became common. Survival meant staying ahead in an evolutionary arms race. The seafloor crawled with trilobites, armored explorers of their age. Up above, formidable predators like Anomalocaris lurked, with its knobbed eyes and grasping appendages. Simple sponges filtered water, while odd ribbon worms tunneled through the mud. Though none of these exact animals survive today, their designs echo in creatures swimming the oceans now. Even at this early point, real ecosystems were forming, chains of predators and prey, competition for food, surprising partnerships. Life was no longer a random soup of simple forms. It was strategy, defense, and the start of battles that have never ended. Evolution had hit the fast lane, and nature never looked back. Yet, even with so much happening, our story is still ocean-bound. For countless millions of years after the Cambrian diversity bloom, life remained stuck in water. Land, though vast and dry, was untouched, an empty canvas of rock and sand. It wasn't that terrestrial life was impossible. Nothing had cracked the code for surviving out of water's embrace, where sunlight, dryness, and gravity challenged every attempt. The sea was still the safer bet, a gentle cradle shielding fragile forms. Eventually, life's next leaps came from unexpected corners. Plants or their ancient predecessors dreamed of land first. But before any root-gripped dirt or limb set down, the oceans continued spinning their own epic saga, full of twists that set the stage for everything after. To truly understand how extraordinary life's rise was, you must see the stage it began on. Before any creatures, before the first ripple of biology, Earth itself was alive, but not the way you might think. Young Earth was rowdy and wild, its surface boiling and shifting, its core ablaze. If you could travel to those early days, you wouldn't recognize our world. Breathing would be impossible. Standing outside would last seconds, and still this brutal chaos would one day become the only home we know. Let's jump even further back, beyond human memory, past any fossil, straight into deep ancient time. Around 4.5 billion years ago, Earth took shape. It was born inside a swirling cloud of gas and dust, circling a young star. The planet grew piece by piece, as rocks, metals, and dust crashed into one another. Violent impacts that turned the planet into a ball of fire. Some collisions were tiny, like grains of sand sticking together. Others were cataclysmic. One giant impact, possibly the biggest, involved a Mars-sized body colliding with Earth. The aftermath changed our planet forever. From that chaos, debris flew into space, eventually gathering to form the Moon, a silent companion that still pulls on our oceans and lights our skies. That shining light is a scar, a relic of planetary violence. Even after the mayhem of creation, Earth wasn't peaceful. Its surface was a seething sea of molten stone, bombarded by volcanoes spewing toxic gases into a choked sky. Continents didn't exist yet. Oceans were only a future dream. The crust formed and shattered repeatedly, shuffling like an unfinished puzzle. After millions of years, things began to quiet. The outer shell cooled and the sky, filled with thick steam, finally unleashed epic rains. These weren't showers, but endless torrents, downpours that may have lasted centuries, gradually filling cracks and low spots to form the earliest oceans. Where did all that water come from? Some of it bubbled up from minerals deep inside the planet. Some arrived frozen in comets, icy messengers from far away. If you could look at Earth back then, you wouldn't see blue skies or clouds, just a haze of poisonous chemicals, carbon dioxide, ammonia, methane, and nitrogen hanging thick in the air. There was no oxygen, and ultraviolet rays blasted the ground. Lightning storms were constant. Nothing about the world was safe for us, yet for chemistry, it was paradise hot, active, and ripe with possibility. Scientists call this the prebiotic Earth, a place where biology hadn't started yet, but the ingredients were all swirling together in wild abundance. Warm pools steamed along volcanic shores. Deep-sea vents gushed hot minerals. The planet churned with energy, minerals, and light, everything needed for something to happen. Within this restless landscape, the first seeds of something new began to stir. It wasn't alive, not yet, but a chemical pattern, a little echo of persistence in the chaos. The moment between non-life and life is hazy, especially at the very beginning. For life to appear, the first molecules had to learn to make copies of themselves before falling apart. How did this happen? It's still one of science's big mysteries. One idea is the RNA world theory. RNA, a close cousin of DNA, is a molecule that's simpler but powerful. It can carry instructions and sometimes help control chemical reactions. Some scientists think that, just by chance, the right RNA molecules might have formed in Earth's bubbling soup. Remarkably, a few of these might have been able to copy themselves. At least a little is this rare, absolutely. But when you have billions upon billions of molecules and millions of years, even the rarest chances add up to certainty. Another leading theory puts these first steps near undersea hot springs. Deep ocean vents shoot out mineral-rich superheated water, creating fierce gradients and non-stop chemical mixing, perfect for new experiments. These spots could have protected and powered the first big leaps toward life. Either way, the recipe was the same: chemistry driven by natural forces, slowly stumbled, experimented, and eventually nudged its way into biology. Over time, the most successful molecular patterns built tough barriers, tiny membranes to keep the precious parts together, safe from the wild world outside. The first living cells appeared, Simple, delicate, solitary, yet they marked a new era. No longer passive players, these microscopic pioneers learned how to grab energy, grow, and split into copies of themselves. Life had officially started, silently, invisibly, but without ever hitting pause. If you could somehow stand on Earth as this was happening, you'd need gear far tougher than anything humanity's built. You wouldn't notice anything at first. The planet looked empty, with no forest, no fish, and nothing any bigger than dust. But hidden beneath the surface of those early seas, something revolutionary was underway. Life had entered the scene, and these tiny new arrivals would end up staying for an unimaginable length of time. The world's first players were single-celled prokaryotes, the earliest bacteria. No fancy structures, no nuclei, just the basics, but they were champions of survival. They absorbed chemicals floating nearby, gathered in clumps, drifted wherever the currents took them. They weren't on their own for long, though. As generations passed, new varieties developed. Some learned to eat different chemicals, others invented ways to harvest sunlight for energy. The real game changer was photosynthesis, a skill allowing them to turn sunlight, air, and water into food. You might know that plants release oxygen, but long before any plant appeared, the true trailblazers were cyanobacteria, tiny blue-green microbes that mastered the art of making fuel from sunlight. As they produced energy, these bacteria started exhaling oxygen as a byproduct. At first, that oxygen met iron in the oceans, rusting it and sinking to the bottom. But over time, more and more oxygen entered the air. For most early life, this wasn't a welcome change. Oxygen is highly reactive and can kill anything not ready for it. So as oxygen grew more common, huge numbers of old life forms vanished. Some, however, managed to adapt, learning either to hide from oxygen to resist it, or better yet, to use it. This immense drawn-out shift, spanning hundreds of millions of years, is called the Great Oxidation Event, not a single disaster, but a slow, violent transformation. Earth was being rewritten by its tiniest inhabitants, and the drama of life was growing with it. At the same time, Earth itself was transforming. Continents started forming, plate tectonics pushed and pulled crust into new landscapes. Mountains rose and crumbled, volcanoes spread new land. The ground was always on the move, and life, simple as it was, followed right along. We don't have many fossils from this early period. One-celled creatures rarely leave anything to find. But some built structures, stromatolites, ancient layered rocks made by generations of microbes. You can still see these living fossils in places like Shark Bay, Australia, evidence of an age more than 3 billion years vanished. Stromatolite mounds grew where colonies of bacteria trapped sediment, building them up, layer after slow layer, century by patient century. These landscapes weren't lively, but they were persistent. Imagine coastlines lined with these ancient microbial towers beneath shallow, calm seas. No fish, no footsteps, just quiet, continuous work. Life's mark was slow, nearly invisible, yet unyielding all the same. Back in those days, time itself felt different. Days whipped by in just about 18 hours. The moon hanging much closer to Earth made tides enormous. Storms and patterns moved by rules lost to history, shaped by gases utterly unlike what we breathe now. Still, through every change, life pressed forward. If it seems like this part of the story crawled rather than rushed, billions of years without animals, flowers, or any familiar excitement, that's because it was a preparation phase. Biology was sharpening its tools, new ways to store and use energy, more advanced genetic codes, building blocks for ambitious futures, all quietly developing beneath the water's surface. For the time being, though, Earth's kingdom belonged to microbes. No eyes, no brains, no legs. What they had was time far, far more than any modern creature could imagine. Time to adapt, to experiment, to wait for bigger breakthroughs. Eventually that breakthrough would arrive. Cells would get more advanced. Some would start teaming up. The rise of multicellular life was still in the far future, and the route there was never straight. Evolution is about experiments, flukes, and rare strokes of luck that stick around. So while oceans stayed the world's main event, teeming with silent promise and opportunity, all the real drama happened in miniature. Think about visiting Earth 3.5 billion years ago. There'd be no sound, no birds, no insects, not even the breeze in leaves, because there were no leaves. Silence wouldn't just be quiet, it'd be the absence of everything that ever made noise. No footsteps, no breaths, no rustling. The world itself was in motion but without an audience. Heat shimmered from volcanic vents, tides crashed into empty shores, meteorites sometimes lit up the sky, events unwitnessed, unnamed, and unremembered. But just beneath the surface near ancient coasts, life's quiet revolution was underway. Shallow water seemed lifeless at first glance, sometimes cloudy, sometimes crystal clear with minerals. Yet between tiny sand grains and clinging to bold rocks, basking in sunbeams, the first real biological communities had started to form. Not animals, not plants, only cells, microbes far smaller than dust, living out their cycles without sound, sight, or thought. Yet they were anything but idle. These first biological settlers, primitive bacteria and archaea, built the foundation for our world. For more than 2 billion years, they had the stage to themselves, and they did much more than just hang on. They redefined the planet itself. Some fed on available chemicals, hydrogen, iron, sulfur, even methane. They dominated environments most life today could barely survive. Acidic pools, boiling springs, seafloor vents. Even now, their descendants cling to existence in such harsh spots. We call them extremophiles, but in the ancient world, these places were the norm. With no competition from anything more complicated, microbes filled every crack and corner, churning through the mud of shallow lagoons, spreading inside porous rocks, forming thick mats of many kinds living together. Some species created waste which others used as food. Some provided structure, while others moved nutrients. These weren't just mindless gatherings. They were the world's first bustling ecosystems, ancient cooperative living that set the model for all that followed. Over time, more of these microscopic adventurers discovered new talents. Among them, a version of photosynthesis. It wasn't anything like what green plants do now. Many used not water for photosynthesis, but hydrogen sulfide or other chemicals capturing energy from light in different creative ways. This new approach to capturing energy gave its inventors a major advantage. Microbes able to harness sunlight for fuel could spread quickly in sunlit waters, grow in numbers, and carve out new territory. Around 2.5 billion years ago, an even bigger breakthrough appeared: oxygenic photosynthesis. This revolutionary trick used water as an electron source and released oxygen as a side effect. The main stars of this leap were cyanobacteria, tiny aquatic microbes often mistaken for algae but not actually related. Though minute in size and unimpressive in appearance, these early cyanobacteria kicked off one of the most dramatic shifts in the planet's history. As their populations boomed, they began flooding both oceans and air with oxygen. At first, this oxygen was quickly tied up, reacting with iron in the water and creating thick blankets of rust that settled onto the seafloor. These telltale layers, called banded iron formations, still exist in ancient rocks, a time capsule showing where microbial life was quietly reshaping the globe. Eventually, oxygen levels grew beyond the sea's ability to soak it up. It started collecting in the air, and the world changed forever. For nearly all life at that point, oxygen was poison. It shattered proteins, broke down cell membranes, caused damage that most simple cells had no way to repair. Rising oxygen meant mass die-offs as countless organisms went extinct, some escaping to places where oxygen hadn't yet reached, a few managing to adapt. For the first time, life faced a threat that wasn't a volcano or a meteor, but a byproduct from its own kind. The Great Oxidation Event wasn't a quick disaster. It unfolded over hundreds of millions of years, but it transformed everything. The sky's color changed. New rocks and minerals filled the earth. The climate shuffled its patterns. And with that, the stage was set for entirely new possibilities. It's easy to overlook these ancient bacteria and archaea. They're invisible. They seem simple, but calling them primitive misses the mark. These tiny survivors were the most inventive, adaptable life the world had ever seen. They could survive frozen deep in Antarctic ice, thrive in boiling hot vents on the seafloor, live in radioactive waste, and float at the edges of the upper atmosphere. Some could pause their lives for centuries, others could eat metal, a few could even withstand the vacuum of outer space. On the turbulent early Earth, these traits weren't oddities, they were requirements. Volcanoes erupted, meteorites still rained down from above, oceans shifted, and climates whiplashed from one extreme to another. Through all these changes, microbes adjusted on the fly, trading genes, forming protective spores, changing metabolisms to fit whatever the planet threw at them. Evolution was already a game of flexibility, billions of years before bones or brains. Despite lacking nerves or senses as we know them, these early organisms could sense and react to their world. They drift toward nutrients, shift away from toxins, all through simple chemical signals. Some started building internal frameworks and storage compartments. Others began to cluster in close groups, creating protective biofilms that shared resources and shielded against danger. Within these tight-knit collectives, the beginnings of true teamwork emerged. Was there intelligence? Not even close, but there was feedback. One cell would release a chemical message. Neighbors would respond, and together, they'd change their environment, sculpting tiny habitats, trapping sediment, redirecting currents, or building rocky shelters for future generations. Those layered rock domes, known as stromopolites, were more than just fossilized colonies. They were evidence of how bacteria weren't just scraping by. They were busy transforming the very planet they lived on. Over millions of years, their combined work remodeled Earth into a place that could one day support something greater. Not because they aimed to, but simply by existing in vast numbers for immense stretches of time, using the right chemical toolkit. Most of these early species left no traces we can see. The only evidence is the rare microfossil in ancient rock, or subtle chemical hints like odd carbon and sulfur isotopes. The true spectrum of ancient life is mostly lost, but its impact is in everything that came next. Eventually, the most successful microbes didn't just drift or huddle. Some evolved new inner parts, membranes, compartments, and eventually nuclei. This leap from simple prokaryotes to complex eukaryotic cells was a gigantic step. Bigger cells meant more control, richer chemistry, and the potential for new ways of life. It was the moment when biological tools unlocked much more potential. Still, this transformation was a long, slow process. In the microbe-ruled world, evolution didn't need to rush. Oceans ran deep, sunlight and energy pulsed across the waterways, and there was plenty of room for experimentation. As oxygen levels rose, the world itself became trickier to live in, more stable in some ways, but more demanding in others. Some ancient microbes figured out how to detoxify oxygen, inventing enzymes that neutralized its harsh effects. Others, even more remarkably, learned to embrace it. They figured out aerobic respiration, a much more powerful way to extract energy from food. Any creature that mastered this trick could suddenly fuel much larger, faster changes than before. And here, quietly, the early steps toward complexity began. Cells became more intricate, developed more parts, and forged more links and interactions with each other. Eventually, the first real cooperation arose, not in the way we think about teamwork, but as actual organisms living inside others. In one incredible twist, a bacterium moved inside a larger cell, formed a lasting relationship, and over time turned into what we know today as the mitochondrion, the engine inside every complex cell. This exceedingly rare event became the spark behind all complex eukaryotic life. But that jump was still ahead. For most of Earth's existence, microbes weren't just the background, they were the main act. And even now, despite all the spectacular animals and plants we see, microbial life still makes up most of what's alive, both by number and mass. Your own body hosts more bacterial cells than human ones. They're not just along for the ride, they are essential parts of the living system. Rewind to billions of years ago, and they were the only show on Earth. No skeletons, no shells, no senses, just simple cells spinning through oceans, dividing endlessly, listening for chemical cues and responding to light, warmth, and nutrients. Not much to look at, maybe, but they were powerful enough to reshape the entire planet. They built a foundation that every later species, including us, would rely on. Microbes ruled Earth's story for incomprehensible stretches of time, silently refining, experimenting, and developing the raw materials for every leap forward to come. All this time, the oceans remained their vast world. But under the surface, something new was quietly building, the perfect conditions for true complexity. Now the oxygen was finally available. Energy sources abounded. The blueprints for future bodies and behaviors were swirling together, still rough, ever-changing, slowly laying out what would become possible. Very soon, the ocean wouldn't just house drifting cells and films. It would burst with creatures that could move, not just float, but truly swim, chase, evade, and build new worlds inside themselves. Bodies would become elaborate. Competition would heat up. For that to happen, though, life first needed to learn true collaboration. Evolution isn't about straight lines. For most of time, Earth was a world of simplicity, microbes multiplying, clinging to rocks or drifting freely, feasting on whatever chemistry was handy. No predators, no running, just routine and repetition for eons. Then quietly, a new molecule started entering the planet's air, not all at once, not dramatically, but one microbe at a time: oxygen. Today we think of it as life itself, fresh, clean, sustaining. But in those ancient ages, oxygen was a threat, something the earliest life forms never meant to introduce. These ancient microbes didn't have a plan or purpose. They just kept doing what evolution had wired them to, capturing sunlight's energy through photosynthesis. With every cycle, they pulled in carbon dioxide and water, releasing oxygen as a discard. This oxygen didn't just vanish, it steadily accumulated. The main players were cyanobacteria, whose colonies filled shallow seas and blanketed the seabed in thick living carpets. Layer by layer, they grew, trapping bits of sediment and always reaching slowly upward towards the sun. Above them, all might have seemed calm, even serene, but their silent work was rewriting the atmosphere itself. In the earliest stages, the oxygen these microbes made never reached the air. It bonded instantly with iron dissolved in seawater, producing reddish rust that drifted to the ocean floor as sediment. This process went on for millions of years, building up massive bands of ironstone, ancient, layered records that still survive in Earth's oldest rocks. These banded iron formations are the fingerprints of a world trying to adjust to a strange new chemical. But eventually, the planet's huge supply of dissolved iron was used up. There was nowhere left for the oxygen to go, so it began to build up in the oceans and, from there, in the sky. This shift, known today as the Great Oxidation Event, hit roughly 2.4 billion years ago, and it threw life into turmoil. Almost everything alive had evolved in a world with barely a wisp of oxygen. Suddenly, this reactive gas invaded their environment. Inside cells, oxygen ripped apart molecules, disrupted vital chemical systems, and created what we now call oxidative stress, molecular damage from unstable oxygen compounds that shredded proteins, broke DNA, and weakened delicate cell barriers. For most living things, the effect was catastrophic. Populations plummeted. Entire ancient ecosystems collapsed, not with a bang, but over millions of years in a slow struggle for survival. This wasn't one quick extinction, but a long period of suffocation as life either adapted or retreated away from oxygen's dangers. Some microbes vanished into deeper sediments or oxygen-free underwater refuges. Others gradually developed new chemical defenses, enzymes that could repair or prevent oxygen's destructive effects. And in time, some did something truly amazing. They learned to use oxygen itself, not merely surviving its presence, but channeling it to burn food for energy. Switching from oxygen-free anaerobic to oxygen-using aerobic life was a complete game-changer. Aerobic respiration is far more efficient, generating much more usable energy. The cells that cracked this trick could move faster, grow bigger, and build more sophisticated structures. Suddenly, evolution's possibilities exploded. But this supercharged metabolism demanded tighter control. Cells needed to invest in antioxidants, manage their interiors better, and build stronger, more selective membranes. Oxygen's arrival forced life to become more organized and complex. Meanwhile, the broader environment was changing too. As oxygen spread, it reworked the entire planet's surface. Rocks weathered differently. Elements like nitrogen and sulfur began cycling in new ways. New minerals appeared that couldn't have existed before. Most important of all, the rising oxygen gradually led to the creation of Earth's ozone layer, a fragile but crucial shield high in the sky, formed from oxygen molecules linking into triplets. This ozone filter absorbed the sun's harsh ultraviolet rays, making the planet's surface less hostile and eventually welcoming enough for life to begin exploring land. At this point, though, nearly all the action remained underwater, as the oceans were still life's main cradle and forging ground in a world in the midst of an epic transition. No one knows for sure when the very first oxygen users appeared. It likely happened many times, not in a single moment, but through slow, scattered innovations. Early cells took in bits of other microbes, developing internal structures to handle the new oxygen-rich chemistry. These partnerships laid the blueprint for complex eukaryotic cells, organisms that could manage energy with awesome efficiency. Oxygen didn't just make complexity possible, it made it likely, but the path was anything but smooth. Oxygen levels rose, then leveled off. Vast stretches of Earth's history, the so-called boring billion, passed as the atmosphere stayed stuck in a low oxygen state. There wasn't enough for big, fast animals, but there was plenty to drive microscopic innovation. Some call this a boring era, but that misses what was really happening below the surface. Modern cell biochemistry was being sharpened and perfected. Life was testing new forms, new behaviors, and pioneering symbiotic relationships. The slow groundwork for multicellularity and specialized tissues was underway, with oxygen as both a challenging filter and a transformative fuel. Eventually, oxygen levels tipped higher again. Earth cycled through ice ages, and as habitats shifted, life didn't just adapt with small changes, it boomed with new invention. Eyes, shells, jaws, arms, and legs. These upgrades demanded more energy, faster responses, and higher competition. Complexity meant pressure, and pressure meant evolution would accelerate. But for all this to happen, cells first had to learn to genuinely collaborate, to specialize, to cooperate, to weave themselves into single complex organisms. They would form skin, nerves, muscles, and entire organs, the very hallmarks of animal life. That twist in the story was only possible thanks to what had once been seen as a deadly mistake: oxygen itself. Once oxygen settled in the atmosphere, Earth didn't fall silent. Life adapted and diversified, finding new strategies to thrive in the changing chemistry. But before there was anything with muscles, nerves, or organs, Earth saw construction on a different scale altogether, not with bricks or steel, but with biological blueprints, unlike anything we know. Microbes teamed up to build dense mats, thin but resilient layers only millimeters thick, grown slowly by communities of interdependent cells. Some species fixed carbon, others controlled nitrogen. Some microbes took on the role of breaking down waste, turning complex chemistry into simple structure. Layer after layer, these microbial communities worked together, interacting with their surroundings in ways that left permanent marks. As particles settled onto microbial mats, the mats grew up and over them. Year after year, more debris arrived while new layers formed on top. This slow repeating pattern eventually created domes and columns, the ancestors of what we now call stromatolites. Stromatolites aren't hidden relics. They punctuate ancient rocks over 3 billion years old, popping up from Australia to South Africa, Greenland to Canada, all places where the oldest crust survived upheaval. When sliced open, these formations reveal frozen ripples, sometimes twisting or branching, like geological fingerprints from another age. To geologists, stromatolites are instant giveaways from the past. To biologists, they're time capsules, built not by individuals but by entire microscopic ecosystems. Every thin mat represented a rich, dynamic network, bacteria and archaea feeding, cycling energy and jostling for light and nutrients. Microbes in these mats didn't talk to one another, but their entire chemistry was connected by invisible rules of survival. Each layer created leftovers that the next group needed. Those living near the top thrived in oxygen's presence, while just below, species survived in near-oxygen-free darkness. Gradients, subtle shifts in pH, temperature, and chemicals, enabled dozens of species to thrive together in a slice thinner than a fingernail. That structure, though not intentional, made these mats resilient. As conditions shifted, some layers died off and others grew in, but the overall framework persisted. Even now, modern stromatolites survive in a few special places. Shark Bay in Western Australia is famous. The water there is so salty that most grazing creatures stay away, letting the microbial mats build undisturbed, almost exactly as they did billions of years ago. Layer by layer, they trap sand, pile up new surfaces, and slowly solidify into rocky mounds. At a glance, you'd mistake them for weather-beaten stones, battered by wind and tides. Yet beneath the surface, the ancient chemistry continues: photosynthesis, carbon capture, sulfate reduction, the same processes their ancestors used. This isn't nostalgia, it's living history. Back in the planet's early eons, these microbe cities must have carpeted shorelines, filling shallow basins and extending wherever nothing larger came to break them up. They shaped the seafloor, affected how sediments flowed, trapped nutrients, stabilized shifting ground in an unpredictable world. And in the top layers of these mats, cyanobacteria started producing oxygen, gradually transforming the air and driving the great oxidation event. The architects of Earth's first buildings were also the makers of its first breathable atmosphere. They didn't plan their work or admire it, but their creations are still visible today. Elsewhere on early Earth, in hydrothermal vents, steaming hot springs, or the oxygenless depths of lakes, different types of biofilms and microbial mats formed, each with their own creative style. Some oozed slimy glue to hold sediments together. Others precipitated minerals straight from water, creating crusts, balls, or branching mineral webs. When preserved, these patterns form what scientists call microbials, a broad family that includes stromatolites and other weird, beautiful structures called enchrolites, thrombolites, and dendrites, each shaped by its growing conditions. For paleontologists and geobiologists, these layered and branching textures offer precious clues. They show how life left its mark on rocks long before skeletons or shells. More revealing still, they prove a powerful point. Life doesn't just adjust to the world, it changes the world. Sometimes the effects are subtle, sometimes profound. Earth's first great builders didn't use tools or blueprints. They constructed by living, layer after patient layer, metabolism after metabolism. As these mats and films grew, they started changing marine chemistry, shifting pH, controlling how nutrients and ions moved, and even creating special microhabitats where entirely new reactions could unfold. These weren't meaningless side effects. They were feedback loops, with life and planet shaping each other again and again simply by existing. We may never know the true diversity of those early worlds. DNA disappears over eons, but by studying today's microbial colonies in hot springs, salt flats, and hydrothermal vents, we can imagine ancient mats filled with dozens or even hundreds of species. Some worked together, some competed, all responding to changes in sunlight, salt, and the flow of raw materials. These mats weren't unchanging. Entire communities migrated upward or sideways as sediments shifted or new territory opened up. Some microbes turned into spores, hitching rides on currents and settling in distant lands. Others floated as plankton, at times forming vast blooms across the sea's surface. Even now, microbes rule in numbers and variety, though most people only notice them during outbreaks, blooms, or when something gets sick. But their legacy is everywhere, shaping soil, building coral reefs, cycling minerals in caves, even etching stone on modern buildings. All of it echoes the ancient skills of mat-forming microbes still going after all these ages. Billions of years ago, this wasn't just background noise, it was the entire story. What could be built without thought or plan ended up transforming the planet forever. The impact was enormous. Microbial structures assembled not only foundations for life, but actual physical layers, carbonate platforms that would one day rise up as mountains. They built stable ground for newcomers, altered the air, and set the stage literally for all that followed. It all started with mats and domes and colonies, and slowly Earth's oceans began to fill with larger, more sophisticated shapes. Not everything arrived at once. Change was gradual at first, but then innovation accelerated. The first eukaryotic cells, loaded with new internal tools, emerged right inside environments crafted by microbial communities. In those ever-shifting waters, some cells began sticking together, not by accident or simply for a short while, but as a whole new strategy joining forces, as one living unit. That idea, multicellularity, opened doors for life's next giant leaps. New forms developed, new ways of organizing, and teamwork at the cellular level flourished. Meanwhile, the original builders, the mapmakers and slime architects, didn't disappear. Their creations remain locked inside the very bones of the earth, shaping the seas that led to every complex creature ever to rise. For something that started out as slime, it's a remarkable legacy. For eons, life kept to a tight script. Single cells held absolute rule over the oceans, some floating, some building mats, but all living on a small scale. Simplicity was the norm. Nothing more complex was possible. Cells could evolve internally, swap genes, unlock new chemical tricks, but most lived and died alone. Then something changed. The shift wasn't fast, but compared to the long calm of earlier ages, the pace of life's evolution picked up. Structures gained new complexity. Cells began cooperating beyond anything before, and bodies took shape: fronts, backs, mouths, tails, eyes, limbs, and shields, where none had been seen a few 100 million years earlier. Then, in what amounts to a brief burst on the planet's vast timeline, the oceans erupted with forms the world had never encountered, and many it would never see again. This era, the Cambrian explosion, almost sounds violent, but don't be fooled by the name. There were no literal blasts. Instead, what happened was a sudden, spectacular increase in diversity and complexity that left a permanent mark on the fossil record. Around 541 million years ago, creatures began evolving hard shells and skeletons. For the first time, movement became truly coordinated, and the business of hunting and being hunted began in earnest. Before this turning point, nearly all living things were soft-bodied, drifting or stuck, most just filtering food or soaking up sunlight. Hardly anything stalked or chased prey. With so little danger, there was barely any reason for armor or defense. That all changed when evolution's arms race kicked off. Some life forms evolved ways to move and sense their surroundings, and suddenly, being able to eat or avoid being eaten became urgent. Shells and spines appeared. Creatures learned to dig, hide, and blend into their surroundings. Eyes developed for the first time. Each adaptation ramped up the tension. New hunters demanded new, better defenses. Natural selection became a constant, pulsing tug-of-war for survival, with strategies evolving on both sides, often at a breakneck pace. Trilobites became the poster children of this era. They were relatives of today's insects and crabs, with segmented bodies and tough outer shells. Some had spectacular compound eyes, some grew long, armor-like spines down their backs. Fossil beds around the world have yielded countless trilobite shapes and sizes, from tiny thumbnail scuttlers to giants stretching over 25 centimeters, making them some of the sturdiest and most common remnants of the Cambrian world. But the oceans also hosted far stranger creatures. Anomalocaris, a flexible, undulating predator, hunted with big complex eyes and menacing claws, its mouth a circular trap lined with stiff plates, like a sharpened pineapple ring that could grip and cut. It was among the sea's first large hunters, efficient, quick, and utterly unfamiliar. Then there was Hallucigenia, a skinny tube of a worm that bristled with spines along its back and dangled tentacle-like legs beneath. For decades, scientists couldn't even tell which end was which, often drawing the creature upside down, and its name fits, inspired by its weird, dreamlike looks. Opabinia took things further, sporting 5 stalked eyes scattered across its head, and a long hose of a snout that ended in a claw for grabbing prey. Segmented and paddle-shaped, it glided just above the seafloor, a body plan so unique that nothing alive today compares. Wewaxia, another oddity, looked like a flat, scaled slug with a covering of leafy plates and bristling spines. It likely lived on microbial mats, scraping up meals with a rough tongue studded with tiny teeth. What connected these strange organisms wasn't just how bizarre they looked, it was their inventiveness. Each was a living experiment, a new body plan or survival tactic. Many of these early designs prospered, giving rise to descendants in later ages. Others became ancient dead ends, vanishing forever. Why did this surge of complexity happen when it did? Scientists are still searching for the answer. Some believe a rise in oxygen made higher energy lifestyles possible, fueling bigger bodies and faster metabolisms. Others point to escalating ecological interactions, predators, prey, competitors, all pushing each other to evolve new solutions. There may also have been sudden genetic breakthroughs, like new master genes turning on more inventive body structures. Whatever the cause, the Cambrian world was now a riot of innovation. Every ecological strategy in play, from ambush predator to armored grazer, from burrower to swimmer, from filter feeder to lurking scavenger. This period wasn't only about predators charging through the water. Many creatures spent their days hidden deep within sediments, avoiding danger by simply vanishing from sight. Some evolved flattened bodies, sneaking under visual hunters' radar. Others left the safety of mats, instead catching floating particles as food. Life branched out in every imaginable direction. Hard shells and exoskeletons gave these animals a greater chance of being preserved, so now the fossil record suddenly exploded with detail. Even soft-bodied species left delicate imprints, especially in legendary fossil sites like the Burgess Shale in Canada, Chengjiang in China, and Sirius Passer in Greenland, where extraordinary preservation captured everything from muscles to gut tracts, even patterns of ancient eyes. These fossils are time travel made real, revealing not just bones but snapshots of whole communities. You can see what hunted, what hid, what scavenged, what simply filtered the water, all layered together in a vivid ancient ecosystem. And this biological leap didn't mark the first appearance of multicellular life. Simple multicelled organisms had already existed for millions of years. What changed was scale and complexity. Tissues with special jobs, nervous systems to sense the world, muscles coordinating for purposeful motion, and eyes beginning to send signals to primitive brains. Suddenly, behavior mattered more than ever. Life wasn't just about surviving as a blob or a filter. What you could do, how you moved, and how you reacted became far more important. The Cambrian set the blueprint for animal activity, but its effects didn't end there. Later eras would push these breakthroughs further, refining and reworking every newly invented idea. For the first time, life in the ocean wasn't just present, it was self-aware, at least in a basic sense. Creatures noticed each other, chased and escaped, competed, and in many cases thrived. The oceans never returned to simplicity. Life on land was still in the future. For now, only oceans held such drama. But beneath the waves, the seafloor changed forever, from a simple landscape of mats and mud to a tangled web of gardens, hunting grounds, crowded crossroads. Space and food suddenly became precious. Survival fueled competition, and competition fueled evolution. And in this new complexity, another vital shift was underway. Some animals were about to develop the strength to support their bodies, to reach out or burrow, and eventually to leave the water altogether. But before that, reefs and new kinds of communities took root. As the oceans crowded with burrowers, crawlers, and hunters, another subtle yet hugely important trend was beginning: the widespread evolution of vision. Among all these new creatures, more and more developed the ability to sense light. It started simply, a patch of light-sensitive cells able to warn of changes in brightness. No way to see shapes or focus, just to tell if something passed overhead, or if day was merging into night. Even so, this sneak peek at the world was a game-changer. Over time, light sensors deepened into pits that could detect direction, then into cups that sense shadows, and eventually into tubes and eyes with true lenses. Suddenly, shapes and movements snapped into focus. The arrival of vision changed life forever. Where once everything depended on chemical cues and touch, now survival meant being able to spot friends, foes, and food before they could spot you. For ages, marine creatures depended mostly on chance, on bumping into food, lucking into a mate, or simply reacting slowly to whatever was nearby. Vision changed everything. Suddenly, animals could spot opportunities or threats from a distance. No longer did survival depend on accidental encounters. You could move towards a meal or steer away from danger before contact. Predators got sharper at hunting. Prey became savvier at avoiding a silent stalker. Now shape and movement became signals. Colors mattered. Staying absolutely still was a survival tactic. But so was speed. Among early innovators, arthropods, especially trilobites, pushed eyes to new heights. Some developed intricate compound eyes with scores or even hundreds of tiny lenses forming a curved patch. Instead of a single clear view, these animals saw a mosaic of images, not crystal sharp but exquisitely tuned to motion. In the murky, debris-filled Cambrian seas, this was perfect. Trilobites could tell instantly if something moved nearby or if a shadow fell, letting them dive for cover before trouble arrived. These first visual systems didn't have to be perfect. They just had to be better than no sight at all. Some primitive worms sported mere eye spots, basic patches of light-sensitive cells that helped them tell day from night, while others developed basic lenses for sharpened focus or depth perception. Evolution took many approaches. Some stuck to the classic compound structure, while others pioneered camera-style vision with a single lens focusing images right onto a curved retina, a blueprint vertebrates, including humans, would later refine to brilliance. But seeing wasn't just about tracking enemies or meals. Eyes opened new ways for animals to interact. Visual signals soon became vital for everything from courtship to territory claims. Bright markings, dramatic displays, warning stripes, all depended on the fact that now at last there was someone around to notice. In some groups, sight eventually took over as the main sense, steering movement, feeding, even communication. In others, it faded behind smell or touch, but even then, the presence of vision changed the rules for everyone. Before eyes, most animals lived close to mats and sediment, barely moving, relying on slow, steady flows of energy. Bacteria powered grazers. Grazers fed filter feeders, life was quiet and stable. Once animals began to see, sleepy stability gave way to action. Hunting began, evasion flourished. The structure of the whole community shifted from flat, layered, and slow to dynamic, mobile, and unpredictable. Predator-prey relationships stopped being mostly random and became targeted and strategic. With sight, animals directly sought out food or trouble, ramping up pressure to develop new defenses. Thicker shells, deeper burrows, faster escapes, or trickier camouflage. Fossils show this burst of pressure. Cambrian rocks hold more and more evidence of armor, reinforced shells and deeper tunnels dug by creatures desperate to hide. Open ocean was no longer safe. The seafloor became crowded with animals digging in or dashing away. This in turn pushed predators to grow longer limbs, develop faster propulsion, and invent ever better ways to see. Take Anomalocaris. Its huge, stalked compound eyes packed thousands of lenses. For its time, it may have had astonishing visual power, tracking prey not just left and right, but up and down, across 3D space as it zipped through open water. Even passive filter feeders adapted, learning to close up at the flicker of a shadow. Just having eyes changed the rules for everyone, from speedster hunters to baggy-bottom grazers. But having vision proved to be only part of the challenge. With eyes came the need to process all that new information, integrating sight, movement, and immediate action. It wasn't enough for a creature to notice danger, it had to react, and react fast. This nudged some animals toward new forms of nervous systems, more coordination between eyes, nerves, and muscles, quicker pattern recognition, and ultimately the creation of primitive brains. These brains weren't thinking like ours, but they filtered signals, picked a direction, and made decisions, something entirely new on Earth. More advanced vision encouraged more stirring and darting, which drove evolution to favor better control and planning. Fast movers thrived if they could predict patterns, who's hunting, where to hide, how to hunt back. The ecosystem wasn't forcing life into complexity, it was rewarding any animal that could handle it. Eyes opened brand new jobs for animals, lying in wait in perfect ambush, grazing with a careful eye on the horizon, tracking the angle of the sun, or even adjusting behaviors to cycles of night and moonlight. With eyes scanning from above, hiding flat on the seafloor, or burrowing became a must, while those who stayed soft evolved spines, plates, or even chemical poisons, sometimes signaled with vibrant color. Not everywhere was vision a winning edge. Beneath the reach of sunlight, deep in shadowy trenches, chemical and physical senses still reigned. But in the shallows and open water, eyes became evolution's runaway success, evolving multiple times in different lineages. Arthropods, mollusks, vertebrates, each with its own twist, strengths and weaknesses, all for the same goal, making distance matter and letting animals react to what they hadn't yet touched. True sight meant a new kind of awareness, not thought as we understand, but the power to move with intention, predict what might happen, and interpret a dynamic, moving world. These new tools, seeing, reacting, planning, sped up evolution's pace. The Cambrian wasn't the climax, it was the prologue to endless refinements. Advanced eyes, sharper reflexes, complex behaviors all started underwater, in creatures whose tiny innovations illuminated the world for the first time. The brightness wasn't new, the ability to see it was. Before trees stretched to the sky or trails wove across muddy ground, the entire story of life played out in the sea. This wasn't one single vast open place, but a layered patchwork. Oceans changed with depth, temperature, and current. Every niche was occupied by something different. From sunlit shallows to lightless trenches, life faced a staggering mix of challenges and responded with an even wider variety of solutions. The Cambrian had already shown what could happen when bodies got complicated, but soon these bodies began to fit together, each filling a role, trading energy, and building the world's first ecological webs. In the sun-drenched upper ocean, light powered the earliest food factories. Microbes still dominated these productive layers, but now they were joined by complex eukaryotic algae. These new plankton formed drifting blooms, floating, sun-catching clouds that turned sunlight into food for the entire ecosystem. Small filter feeders ate the plankton, larger creatures fed on them, and so the marine food chain unfurled, linking every level, not by plan, but by the energy constantly flowing from the sun downward. One big transformation in ancient oceans came when flat mats gave way to something new, the first reefs. These weren't the sprawling limestone jungles filled with rainbow fish we know today. Instead, early reefs were modest, built by clusters of spongy animals and simple creatures that could anchor themselves and stick together. By the Cambrian, these pioneering organisms, sponges, early limestone formers, and other builders, began assembling reef-like structures that provided shelter and surface for others. Suddenly, the seafloor had nooks, overhangs, and passageways, perfect for hiding, clinging, or catching food, swept past by the currents. This new landscape became a hotspot for diversity, not just life floating freely, but communities thriving wherever light and protection overlapped. Down on the bottom, trilobites scuttled about, scavenging debris or preying on smaller animals. Burrowing worms wriggled through the mud, churning and aerating the soil, forever changing its chemistry. This constant stirring, bioturbation, reshaped the ground beneath the waves, breaking up older mats, mixing nutrients, and creating new habitats in the process. These little movements, multiplied by millions of individuals, ended up transforming whole environments. In this world, no creature was working together on purpose, but every habit and hiding place influenced life around it. One animal's digging affected a neighbor's eating. The tunnels dug by some provided hideouts for others. The structure from ancient sponge colonies became home to countless tiny filter feeders. Predators and prey forced each other to adapt. Speed, armor, spines, hiding, all driving bursts of new forms and specialization. Evolution radiated outwards, with nature's pressures shaping every move. While some life forms hung out on the sea bottom, others began venturing into the water column above, no longer drifting passively, but swimming, maneuvering to find food, escape threats, or seek mates. Streamlined bodies, fine-tuned movement, and new muscles made this possible. Some swimmers adopted heavy armor, plating themselves for defense, while others shed weight, relying on agility, invisibility, or pure speed to survive. The vast middle layers of the ocean filled with planktonic animals, both grazers and hunters, creating new links between the sun-soaked surface and the mysterious worlds below. Even the deep ocean, out of sunlight's grasp, wasn't deserted. At hydrothermal vents where superheated, mineral-rich water poured from the seafloor, strange bacteria used chemistry, not sunlight, to survive. Colonies of tube worms and clams gathered in these darkness-wrapped oases, drawing their energy from sulfur instead of the sun. In many ways, these vent communities echo how Earth's very first life may have survived, and these ecosystems still exist today, oddly unchanged by the passage of eons. Across all these watery habitats, the evolution of reproduction became a dizzying experiment in strategy. Some animals unleashed clouds of eggs and sperm into the currents, trusting to chance for new life. Others chose more deliberate methods, fertilizing internally, brooding young, even dabbling in early forms of nurturing or protection. How parents had offspring shaped everything from how species grew to how populations weathered storms or predators. Each method tweaked how fast a species could recover or expand. Competition and predation continued to intensify. Eyes got sharper, jaws took shape, limbs adapted for grabbing, tearing, slicing. The prey responded with tougher shells, quicker escapes, or deeper hiding places. The push and pull of these relationships made life increasingly fast-paced and unpredictable. Food chains grew longer, energy zipped through more levels, and ecosystems everywhere grew livelier and more reactive. Still, not all creatures chased or hunted. Many anchored in place, quietly filtering food from the water, moving little. Some retreated far below the mud to avoid being eaten. Others went the opposite direction, exploding in number and overwhelming slower threats simply through force of numbers. An interesting phenomenon called convergence took hold, and nature's best answers began to echo across unrelated groups. Fish, squids, shellfish, all independently found similar solutions: streamlined bodies for efficient swimming, compound eyes to spot motion, tough exteriors for lasting defense. These weren't accidents, but reflections of shared challenges in similar environments. This period saw body plans start to stick: broad types like arthropods with jointed limbs, mollusks with protective shells, and worms streamlined for burrowing or slinking through mud. These basic shapes weren't set in stone, but they proved so useful that evolution kept fine-tuning and repeating them. Ancient Cambrian ecosystems were not simple or stable. They were intricate webs where everything was connected and constantly in flux. Extinctions happened, new species arrived, but even as residents changed, the rules of recycling and survival remained. Debris fed the bottom dwellers. No scrap was wasted. Every bit of energy got passed on, always underwater. Meanwhile, Earth's continents' surfaces watched from the sidelines. There were no plants, no bugs creeping over the rocks. The ground was just stone and sand, swept by weather, shaped by rain, but utterly untouched by life. Everything extraordinary still happened in the oceans, and for eons this was the only arena that mattered. But something was stirring on dry land. While animal kingdoms battled beneath the waves, quieter pioneers began to experiment above sea level. These early colonizers weren't hunters or swimmers, but slow-growing, rooted specialists, photosynthesizers. For most of history, land was a blank canvas carved by elements. No trails, no roots, no green, just bare minerals and empty silence. In contrast, the oceans had been bursting with every flavor of life. All the great leaps, cells with nuclei, mobility, eyes, motion, were inventions of water. Sea life thrived on stable conditions and plenty of nutrients. Land, by comparison, offered none of that security. It was open, exposed, and volatile. Still, slowly, life reached out. This leap from sea to land wasn't a heroic march, but a gradual, scattered effort. At first, the new colonists didn't even move. Microbes and algae, sometimes joined by fungi, clung to damp rock faces, forming thin films or crusts. They lived on sunlight, water from rain and dew, and minerals from stone. This teamwork began to break down the rock, slowly turning it into the first faint traces of soil. As these living carpets spread, they made land ever so slightly more inviting. Eventually, the next step came: green algae. The forerunners of plants began spending more time out of water, still hugging damp or shaded surfaces, but slowly adapting to drier, more difficult conditions. To survive, some developed tougher skins, while others spread flat and low to hug the ground and trap moisture. These earliest land plants didn't grow tall, didn't bloom, and had no roots or leaves. Think of them as primitive versions of modern moss or liverworts. Quietly, they transformed the surface. They photosynthesized, released oxygen, and sheltering the soil below. They also helped cool their immediate surroundings and hold in precious moisture. With time, the groundwork grew richer. Fungi partnered with these intrepid plants, attaching to roots or stems and trading nutrients for sugary fuel. This mutually beneficial relationship, still critical for nearly every modern plant, made both partners healthier and stronger. Not long after, the first animals followed. These weren't ferocious hunters or powerful grazers. but likely detritus sifters and algae nibbles. Picture tiny, soft-bodied arthropods hiding in moist soil, the ancestors of today's springtails and mites, finding their niche among the damp organic micro-world that plants and fungi had begun to build. Early land animals didn't roam far from water's edge. Dry air posed a constant danger. Without waterproof skin or efficient lungs, dehydration was always a looming threat. These creatures could survive only where there was enough moisture, damp mud, shaded moss, and the wet banks of streams and ponds. But even in these limited zones, new opportunities emerged. The first real land crawlers were arthropods, descendants of ocean-dwelling ancestors. Their tough exoskeletons gave them a bit of protection against drying out, and their jointed legs allowed them to navigate the rough, bare earth. Some probably looked like armored millipedes, their long, segmented bodies plodding slowly through a landscape empty of leaves or flowers. Fossils from over 420 million years ago suggest these millipede-like pioneers were among the first to carve out a living on solid ground, probably feeding on rotting plant material and helping recycle nutrients into the developing soil. In doing so, they kick-started more intricate land ecosystems. Other arthropods soon followed: primitive insects, tiny spiders, and their kin. Most kept close to the wet ground, needing humidity to survive, and avoided exposure to the sun's drying heat. There was no flight yet. These early land animals crept, burrowed, and hid. As the land food web expanded, predators emerged. Small hunters tracking their prey beneath stones or inside clumps of moss, steadily building the first terrestrial chains. Meanwhile, in the watery world, vertebrates watched this invasion from afar. Ancient fish had branched out into rivers, deltas, and shallow coastal lagoons. Some began to develop lungs, evolved from air-filled bladders that allowed them to gulp air when water's oxygen was low. Others grew sturdier fins capable of pushing their bodies through muddy shallows. Originally, these adaptations evolved to survive in unstable water, drying pools, temporary swamps, places with fluctuating oxygen, but they brought an unexpected bonus. Fins strong enough for underwater crawling could eventually become limbs. Primitive lungs laid the foundation for breathing air. Among the most remarkable of these transitional creatures were the lobe-finned fishes, the sarcopterygians, with solid bones inside their fins. Over time, their fins developed into structures more like arms and legs, skulls flattened out, necks grew bendable, and tails gradually shrank. Gills made way for lungs. Eventually, a few branched off to become the first land-going vertebrates, not just for short foraging trips or to lay eggs, but to stay. This shift from water to land wasn't a single dramatic leap. It happened over generations, with different species making their own attempts. They faced the weight of gravity, the risk of drying out, and the challenge of moving without water's support. But it worked. By the latter end of the Devonian period, some 360 million years ago, the first proper tetrapods appeared, four-limbed creatures that could not only crawl onto land but live there. They still needed to stay close to water, often returning to breed or rehydrate, but their bodies now fit their new home. Thicker bones, improved lungs, sharper hearing, and tougher skin protected them from desiccation. Land, once alien, was now open to conquest. Back then, terrestrial habitats were nothing like modern forests. There were no flowers, no grass, no trees as we recognize them, just spindly ferns, club mosses, and horsetails. The first forests were sparse stands of tall, simple plants using primitive vascular systems, surrounded by air thick with drifting spores. Insects had shown up but couldn't fly yet, so the sky remained empty and quiet. Still, the template for layered living ecosystems was set. Microbes and mosses crunched the soil, early ferns rooted in swamps, arthropods crawled through plant debris, vertebrates waddled along the water's edge, and below all that, fungi spun hidden networks knitting the earth together. It's humbling to realize how recently all this happened on the scale of Earth's story. For nearly its entire history, our planet's surface was untouched, a wild, barren canvas. Suddenly, in a relatively short span, land welcomed plants, then waves of animals. These first steps set the groundwork for future forests, mountains echoing with bird calls, and much later cities. For now, though, the world on land was quiet, its activity close to the ground, but life was slowly gaining ground. By the time insects and millipedes crept over the sodden earth or stared out from stream banks, plants had already taken the lead, spreading steadily and covering the land. They didn't rush, but their presence made all the difference, creating niches for everything that followed. Early landscapes didn't look anything like our woods and forests today. No colourful canopies, no leafy shade, no insects humming overhead. Even the word tree held a different meaning. These first forests, rising around 380 million years ago, were strange places, filled with plants that looked like something from science fiction. Tall, skinny trunks climbed for light, but there were no broad branches or leaves, just stiff, segmented shoots reaching skyward. The oldest trees belonged to groups few modern plants can claim as relatives. Ancient club mosses, early progymnosperms, the ancestors of seed plants and mysterious forms now vanished forever. Some of these early forest builders, like Archaeopteryx, are recognized as among the planet's first true trees. It featured woody trunks, a spreading canopy, but reproduced with spores, not seeds. Its leaves resembled flattened fronds more than broad modern foliage. Still, this towering plant helped set the pattern for a tree, tall, rooted, perennial complex. Other giants, like Lepidodendron, shot up fast and stiff, with bark-like coverings and geometric branches, dominating swampy carboniferous forests. Their biology was still closer to mosses than to today's oaks or pines. There was little colour or floral splendour in these primeval forests. No blossoms, flowers wouldn't appear for another 200 million years. No edible fruit, no pollinating insects, only spores cast loose on the winds. Even the air itself felt different. Oxygen was climbing, but the atmosphere wasn't what we breathe now. Grass didn't exist. The forest floor was a patchwork of spongy moss, decaying plant matter, and fungus, with roots just beginning to knit real soil together. The earth was still mostly bare rock in many places. And yet these odd forests transformed Earth in dramatic ways. First, their relentless photosynthesis drew vast amounts of carbon dioxide from the air, pumping out oxygen and steadily cooling the climate. This massive carbon shift may have fueled a severe ice age late in the Devonian. The plants didn't mean to spark climate change, but by growing, dying, and decaying, they started locking atmospheric carbon away as never before. Second, their roots grabbed into the ground, slowing erosion, trapping sediments, and making soil more persistent. Rivers carved their courses more slowly, and valleys deepened over generations instead of years. As ancient trees fell into waterlogged swamps and failed to rot away, their remains built up in peat beds. After millions of years under pressure, these beds turned into coal, a story written in black stone beneath our feet, capturing an age when life's impact on Earth reached a whole new scale. These ancient forests brought something wholly new to land: vertical layers. For the first time, animals could do more than crawl across the ground or burrow beneath it. Now they could climb, perch, or vanish among the branches and trunks. Insects started to specialize, not only eating plants but using them for shelter and new ways of living. Some developed specialized mouth parts to pierce stems and sip sap. Others began gliding, eventually leading to the evolution of wings and the first animals able to take to the air. The forest canopy didn't just provide support. Its shade changed everything underneath, creating cool, damp spaces where new kinds of plants could thrive. The first undergrowth formed, not lush and flower-filled, but a layered green tangle of hopeful experiments. Canopy, understory, and soil all began to take shape, even if the forest's features were still a rough draft. Fungi played a critical role during this time. As decomposers, they broke down dead plant matter, recycling captured nutrients back into the ecosystem. Some fungi partnered with plant roots, forming mycorrhizal networks that let both survive and grow taller. These underground connections allowed forests to spread and endure, and even today, most trees quietly depend on fungi linked to their roots. Even so, these new ecosystems were fragile and unstable. Plants hadn't evolved seeds yet. Reproduction still depended on water for spores to travel and germinate. Our forests clung to coasts, floodplains, and riverbanks, where moisture was constant. Dry interiors remained barren, without tough, drought-resistant plants to hold the soil. Arid ground was simply too harsh for life to conquer. Nevertheless, plant life pushed forward. Some began evolving more powerful vascular systems to move water up tall stems. Others produced tough spores or even the first seed-like structures, letting embryos wait in stasis for the right moment to grow. These changes were just beginning during the late Devonian and would bloom in future eras. In these early forests, there were no real leaves or flowers, but everywhere you looked, innovation was quietly underway. Each trunk was a test of how to beat gravity and wind. Each root burrowed into the earth, making new real estate for future life. Every fallen branch or log became food for microbes or fungi, thickening the living layer atop ancient rock. By the late Devonian, the planet looked completely different. Rock faces and riverbanks had softened below green moss and ferns. Root systems changed how rivers wound through valleys and how deep soil could go. Air became richer in oxygen, while carbon was pulled down, locked away in plant tissues and buried in sediments. Landscapes were taking on the kind of complexity that would eventually support massive land animals and much later, creatures with our intelligence. The groundwork was all there, even if the world was still quiet. Forests were thin, and the most dominant organisms were small and cautious. But these new animals were not standing upright or racing through leaves, at least not yet. The next rulers of the forest floor crawled, slithered, or moved by skin and muscle. Some reached astonishing size. As plants filled the land with vertical opportunities and deep shade, the animal kingdom started to follow suit, slowly at first, but then with growing confidence. Forests still had no flowers, birdsong, or the buzz of bees, but the air was humid and alive with spores, ferns, and the soundless hustle of growth. Amid all this quiet transformation, the most dramatic stories still unfolded in the water. With the dawn of the Carboniferous period about 359 million years ago, the conditions were suddenly perfect for something out of a sci-fi epic, a planet of giants. Not in the sea, where old legends swam, but among the land's sprawling swamps, marshes, and dense forests, creatures crept, swam, and sometimes sailed through these damp, misty realms. Some breathed with gills, others with lungs, and a few with both. And across the board, they grew huge. Giant dragonflies, massive millipedes, amphibians the size of dogs or small crocodiles. So why was everything so big? It wasn't one cause, but a combination-rich plant life, sultry climate, and most importantly, an oxygen-rich atmosphere. Back then, air probably held 30–35% oxygen, a third richer than today's 21%. Extra oxygen didn't just supercharge wildfires or speed up decay. It changed how animals functioned, especially those that relied on passive breathing. Insects, for example, breathe through tiny holes in their exoskeleton, with oxygen diffusing straight to body tissues. Normally, this system limits their size. In hyperoxygenated air, however, that barrier vanished. Giant dragonflies with wingspans wider than some birds soared through ancient forests. Their name, Meganeura, literally means large-nerved, and they lived up to it, gliding, hovering, and swooping over ponds, laying eggs on reeds and preying on smaller bugs underneath their massive wings. Millipedes reached lengths over 2 meters, lumbering across forest floors in long armored trains, munching on soft, decomposing plants. Modern millipedes are minuscule by comparison. The ancient ones were imposing but likely peaceful, focused on cleaning up fallen debris. Early amphibians, meanwhile, grew into true monsters. They didn't resemble today's frogs and salamanders. Instead, they looked almost like lounging crocodiles, thick-bodied, wide-mouthed, and splayed flat. Some spent their youth in water and their adult lives on land, hunting smaller prey wherever they could find it. Many topped several feet in length and boasted broad skulls armed with peg-like teeth for ambushing the careless. Still, these huge early amphibians had limits. Their skin dried fast, so they stuck to the wettest environments: swamps, rivers, damp forests. Their eggs lacked hard shells, so reproduction had to happen near water. Climate and terrain helped, with sprawling lowland forests and meandering rivers providing endless breeding grounds. In these ancient landscapes, nothing alive looked much like our modern wildlife. No birds sang, no mammals rustled grass, just the rustle of something huge and armored making its way through a primordial jungle. Predation ramped up complexity. Some amphibians grew stronger limbs or jaws. Others adopted camouflage, their skin mottled to blend in among bark and leaves. But predators weren't the only challenge. Drought, disease, and competition shaped every evolutionary step. Things changed quickly. Eventually, certain lineages experimented with internal fertilization, harder skins, and sturdier skeletons. Evolution's answer to surviving away from water. The biggest change. The invention of the amniotic egg, a remarkable self-contained package with protective membranes, capable of keeping an embryo safe and hydrated on dry land. Unlike modern frog spawn, these eggs could survive out of the water. With them, a new chapter was just beginning. This breakthrough in reproduction, the amniotic egg, unlocked a new world for animals on land. For the first time, creatures weren't bound to water for laying eggs. The earliest reptiles showed up quietly. They were small, quick, and not very imposing, sort of lizard-like and able to hide their leathery eggs in safe, sheltered corners. These new arrivals foraged in the leaf litter, hunting insects, and at first looked like just another little critter among the undergrowth. But their bodies gave them new freedoms. They weren't chained to swamps or streams anymore. They could wander farther, climb into drier places, and stay active much longer. Back in the water, fish kept evolving in their own wild directions. Some armored up with thick bony shields. Others developed enormous jaws for crunching through shells. While early sharks and their relatives began to conquer rivers and coastal seas, still the land was where the true revolution was taking place. For a while, Earth's swampy forests let oxygen-hungry giants, enormous amphibians and insects thrive, but that golden age was short. As the Carboniferous came to a close, the planet's climate shifted. Temperatures fell, glaciers expanded, land dried out, and ancient forests shrank away. With their habitats disappearing, many of the giant amphibians and arthropods faded out as well. The age of big, water-loving animals dwindled, not with a sudden crash but through gradual retreat. Stepping into the gap was a new contender. The first reptiles. They weren't impressive at first glance, just small, cautious, and covered in scales. But their ability to survive away from water changed everything. They could explore new terrain and take advantage of opportunities no amphibian could touch. It would take time for them to rise to true dominance, but with the forests as their nursery, the rest of the land was wide open. Earth's story is marked by waves of disaster. 5 great extinction events have changed everything, sweeping away old life and leaving space for the new. The most iconic wiped out the dinosaurs, but the most devastating came much earlier, near the end of the Permian period about 252 million years ago. By then, the continents had fused into a single supercontinent called Pangaea, a vast, sprawling landmass stretching nearly from pole to pole, with enormous dry interiors and harsh seasonal extremes. Oceans rimmed the edges. The heart of Pangaea was often a sun-baked desert. Even so, reptiles flourished. A new group, the synapsids, distant kin of mammals, dominated on land. Plants kept evolving, with early seed-bearers, gymnosperms, beginning to outcompete older spore-producing plants. Amphibians still held on in the wettest places, and the oceans brimmed with corals, brachiopods, ammonoids, and fish. Then the worst calamity in Earth's history struck, what's now called the Permian-Triassic extinction, or simply the Great Dying. In the blink of a geologist's eye, up to 96% of marine species were wiped out. Around 70% of land vertebrates vanished. Some entire groups disappeared forever, leaving only fossils behind. This wasn't a slow fade, it was a catastrophe, global and merciless. What set it off? It wasn't a single asteroid, but a chain reaction of nightmare events. Deep beneath what is now Siberia, titanic volcanic eruptions ripped through the crust, not just in brief blasts, but massive lava flows pouring out for hundreds of thousands of years. The Siberian Traps, a landscape covering millions of square kilometers in hardened volcanic rock, were born from these relentless eruptions, but the lava was only part of the disaster. With it came toxic gases, carbon dioxide, methane, and sulfur dioxide pumping into the sky in quantities never seen before. CO2 soared, the planet heated up, and ocean temperatures spiked. Rains grew acidic. The very chemistry of sea and sky spun out of balance. As the oceans warmed, they lost their oxygen. Vast areas became deadly anoxic zones, where nothing more complex than bacteria could survive. Coral reefs crumbled. Shellfish and other marine animals vanished in waves. Some species tried to run. Many had nowhere to go. On top of that, methane released from melting permafrost or shifting seafloors poured into the atmosphere, accelerating warming even more. Methane is far deadlier than CO2 as a greenhouse gas, and its sudden release only made conditions worse. On land, plants suffered under acid rain, relentless heat, and changing rainfall. Wildfires became common, forests thinned or disappeared, and animals that relied on abundant vegetation starved. With the collapse of plants, the rest of the food web, herbivores, then carnivores, quickly followed. Insects, usually survivors, also endured catastrophic losses. It's the only mass extinction known to dramatically reduce insect diversity. This extinction didn't hit in a single year or decade, but in geological terms it was sudden. One layer of sediment shows thriving life. The next is nearly empty, with only a handful of survivors and a world stripped bare. Recovery was extremely slow. Fossils from after the Permian extinction show a long pause in biodiversity, with simple, short food chains and only small populations. It took millions of years for complexity to return. The Permian extinction was a hard reset for life on Earth. Some marine invertebrates, dominant reptiles, and plenty of other former rulers were wiped out entirely, leaving gaps that only time could fill. Stepping in, slowly, were the ancestors of crocodiles, pterosaurs, and the earliest dinosaurs, those archosaurs who eventually took over in the newly emptied world. But in the immediate aftermath, things were bleak. The oceans were mostly lifeless. Forests were patchy and thin. Most creatures that clung on were those that could get by on little, tolerate heat, and outlast drought. Today, scientists are still piecing together the causes of this biggest extinction. The Siberian supervolcanoes are central, but the puzzle includes everything from toxic metals and runaway acidity to falling sea levels and broken carbon cycles, each adding a layer of stress on an already battered global system. This time there was no asteroid. This disaster came from the Earth itself, from its own deep processes, showing just how fragile stability can be. For life it was the darkest chapter, but not the last. Some species endured. They evolved to survive harsh heat, frequent drought, and unpredictable climates. In the strange, empty landscapes that followed, life found new ways to adapt. The Triassic period, hotter, drier, and full of surprises, set the stage for a fresh wave of evolutionary experiments. Generalists and survivors began to stretch, reshape, and fill the world's new spaces. Some of these survivors would go on to transform the world, rising up on two legs, stretching out necks, growing horns or feathers, and eventually becoming some of the most celebrated animals ever to walk the earth. But that chapter would open in an eerily quiet world. When the great dying ended, the planet was still and empty, not peaceful but drained. Where rich habitats once flourished, there was only silence and survivors. The only winners were creatures who could take the heat, last through famine, and make a living in desperate times. Burrowers, generalists, and tough opportunists inherited this new Earth, ready to shape the next act in the grand story of life. Evolution never promises triumph to the biggest or the boldest. Instead, it rewards whatever survives the toughest challenge. In the harsh aftermath of the great dying, resilience was the winning trait. The survivors, a handful of reptile groups, most of them small and unremarkable back in the Permian. Among them were the early diapsids, reptiles sporting two holes behind each eye which lightened their skulls and gave their jaws extra power and control. These weren't the rulers of the Triassic world, at least not yet, but they were perfectly positioned to take advantage of what came next. The new Earth was dry, blistering and unstable. The supercontinent Pangaea still held almost all the world's land glued together, creating endless interiors with punishing temperatures. Rainfall was sporadic and unpredictable. Habitats were fragmented and vegetation made a slow comeback. But what this extreme land lacked in comfort, it offered in potential, space, and lots of it. Reptiles with waterproof scaly skin and tough-shelled eggs had a huge edge. Unlike amphibians, they didn't need ponds or streams to breed. They could push into dry uplands, arid valleys, sun-baked plains, places frogs and salamanders simply couldn't follow. Some took the opportunity to grow larger. Others grew faster, each filling gaps left empty by the mass extinction. Over time, these adaptable reptiles split into two main branches, the lepidosaurs, which would give rise to lizards and snakes, and the archosaurs, a group on the verge of rewriting life's rules. Archosaurs themselves split as well. One line headed towards crocodiles and their kin, the other would become the first dinosaurs. You wouldn't have picked them out as future titans. Early archosaurs were lean, fairly small, built for speed and agility, mostly hunting on all fours, but some were already experimenting with running upright. Their hips and ankles pointed toward future innovations, optimized for swift, flexible movement. While life on land was still a patchwork of recovery, these archosaurs became the go-to hunters for much of the age, snapping up insects, chasing small reptiles and standing out as successful middle-tier predators, while other survivors filled out the ecosystem. Synapsids, ancestors of mammals, also lingered, but their dominance was fading fast. Archosaurs, meanwhile, kept tinkering with their body shapes, growing new features and exploring every available strategy. The Triassic period saw reptiles push not just onto land, but into the air and sea as well. Some became agile gliders, leaping from tree to tree with webbed wings of skin. Others dove into coastal shallows, gradually turning legs into flippers, reshaping themselves into the ichthyosaurs and plesiosaurs that would one day rule the oceans. Still, the biggest transformation was on land. Dinosaurs didn't start big. When they first appeared, they were just another small, two-legged creature in a world still ruled by hefty, more established rivals. But they had a key advantage. Their legs ran straight beneath their bodies, not splayed out to the sides like a lizard. That meant efficient movement, longer, faster running, more stable stances, and less energy wasted. Some paleontologists also think they had an edge with improved lungs, perhaps even a primitive bird-like breathing system that gave them endurance their rivals lacked. Their metabolic rates might have been higher, too, not fully warm-blooded, but not sluggish either. This package of subtle improvements, flexibility, stamina, agility, became the foundation for everything they would become. With the world still in flux, dinosaurs slowly began to spread by the late Triassic. Some stayed small and quick, thriving as nimble predators and omnivores. Others began their journey toward larger size, stouter limbs, stronger jaws, and more specialized diets, herbivore and carnivore alike, racing to fill back in the food web. But competition never let up. There were still synapsids holding on, mammal ancestors, squat and night-loving with broad heads. For a while they kept important roles, but the landscape was changing fast. Another extinction event arrived as the Triassic ended, not as brutal as the first, but harsh enough to clear out many of the remaining large amphibians and the mammal-like reptiles. This reset the ecological board again. With rivals out of the way, dinosaurs peacefully inherited the Earth. Their rise wasn't thunderous or immediate for millions of years. They were smaller than a large dog, light on their feet, blending into a wild environment of conifers, cycads, and ginkgos. There was no grass, no flowers, just open woodlands and bare ground, all ruled by a single massive continent with blistering heat, wild monsoons, and punishing droughts. In this world, the first true dinosaurs, descendants of fast, nimble archosaurs probably born in what's now South America, began to adapt and spread. Their efficiency was their secret. Unlike lizards, their hips held legs directly beneath their bodies, giving them stamina and range. Their strong hind limbs, long tails, and upright stance made them built for running, covering open ground as no reptile had before. Also, dinosaurs may have breathed with a one-way flow system in the lungs, much like modern birds cycling fresh air with each breath and making their bodies oxygen-efficient engines. This would have given them incredible stamina, helpful in a hot, tough climate. Not quite warm-blooded, not cold-blooded either, somewhere in between, uniquely prepared for their time. As the Triassic closed, dinosaurs small but tough were widespread, but they shared the world with other big reptilian cousins, like the pseudo-crocodilians who ruled top predator spots in many ecosystems. But then 201 million years ago, another extinction event swept the planet, likely triggered by volcanic eruptions linked to the breakup of Pangaea and dramatic climate swings. It reset much of life once again. Many pseudo-crocodile groups and the last mammal-like reptiles vanished. Dinosaurs, small and spread across many areas, survived the upheaval and for the first time found themselves in charge. In the Jurassic that followed, With their rivals mostly gone, dinosaurs rapidly diversified. Some clung to their nimble, omnivorous roots, bipedal hunters with razor claws and sharp vision, the ancestors of every bird alive today. Others went big, incredibly big. Their bodies grew into giants with thickened legs, soaring necks, and massive bellies, soon to become the colossal, long-necked sauropods. There was even room for the ornithischians, the beaked branch of the dino family, masters of armor, beaks, defense, and in many cases social living. In just a few million years, the world belonged to these remarkable, endlessly changing creatures. Over time, those lineages diversified into all the classic dinosaur forms people know: stegosaurs with their armored plates and spiked tails, ankylosaurs protected in bony armor, horned giants like ceratopsians, and duck-billed hadrosaurs. But in their earliest days, these groups were just starting to experiment, a rough sketch before the details were filled in. By the mid-Jurassic, dinosaurs weren't just surviving, they were taking command. Their world was alive with change. Some thundered across open plains in herds, while others prowled as lone hunters in dense forests or along new coastlines shaped by shifting continents. They adapted to regions with more rain and lush growth as easily as they did to dry belts favoring drought-tolerant foragers and swift-footed predators. There was no single dino blueprint. Every niche had its own specialist. They weren't just multiplying, they were innovating. Fossil beds from this era show evidence for coordination and social lives that go well beyond what most reptiles demonstrate today. Parietal footprints preserved in ancient mud hint at groups traveling together. Growth rings in bones suggest some level of group care, or at least long lifespans within the same communities. Injuries that healed before death reveal individuals survived wounds, a possible sign that dinosaurs sometimes helped one another, or that their resilience was remarkable. These weren't mammals, but they didn't need to be. Their toolkit included agility, surprising stamina, endless adaptability, and the creativity to fill any role the planet asked of them. While dinosaurs staked out land, the seas were claimed by unrelated marine reptiles. Sleek ichthyosaurs zipped through the water, their shapes converging eerily on dolphins. Plesiosaurs, with their snake-like necks and paddle limbs, dominated coastal shelves. Yet on land, dinosaurs were the headline act. As the continents rumbled and cracked apart, Pangaea splitting and rainfall shifting, new borders and microclimates appeared, giving rise to even greater biodiversity. In lush areas, giants could flourish. In drier spots, lean, fast hunters and hardy plants prevailed. Dinosaur bones were engineered for efficiency. Lightweight but strong, their eggs were carefully placed in nests. Their senses were keen, sharp vision, acute smell, and extraordinary balance, tuned for a world in motion. They weren't always the fastest or the strongest, but they were always ready to adapt. That was their greatest asset, and it paid off. For not just a brief moment, but an incredible 130 million years, dinosaurs owned the land. Tyrannosaurus rex may be the most famous, but its time on top was just a short chapter at the very end. Long before T. rex ever hunted, other rulers came and went. The Jurassic belonged to Allosaurus and its kin, agile, muscular theropods designed for speed and slashing rather than brute force. Their hands were far more useful than those of T. rex, tipped with strong claws for holding, raking, and grabbing prey. They lived rough lives, as fossils show broken bones and healed wounds, signs of regular conflict, tough competition, and sometimes survival against the odds. Their prey weren't easy targets either. Towering, long-necked sauropods such as Apatosaurus, Diplodocus, and Camorosaurus shared the same floodplains. These titans stretched 20 meters or more, guts and muscles fueled by relentless grazing. Few predators could bring down an adult, so the old, the injured, or the unwary young were the real targets. Allosaurus itself may have hunted cooperatively. Evidence from trackways hints they sometimes moved in groups, possibly coordinating attacks or simply sharing the same territory. Their skulls and jaws appear built for slicing, not crushing, sharp teeth for deep wounds, air sacs for lighter heads and rapid strikes. Jurassic predator diversity didn't stop with the famous Ceratosaurus, prowled with a horned snout and a long, flexible frame, perfect for slipping through forests and riverbanks. Torvosaurus, heavier and closer to a proto-megalosaur, was a heavyweight hunter across Europe and Africa. Each region sported its own apex. Some evolved for speed, others for raw power, some waited in ambush, others chased prey down. Meanwhile, herbivores fought back. Stegosaurus, brandishing huge backplates and a deadly thagomizer, could shatter bones with a single tail swipe. Fossil record shows predator injuries that prove these defenses worked. Group behavior, size, and armor tipped the balance, keeping predator and prey locked in an evolutionary tug-of-war. As the Jurassic faded and the Cretaceous began, the lineup of top predators shifted. Allosaurus and its relatives gave way to new and sometimes even bigger hunters. In South America, Giganotosaurus rose as a predator longer than T, Proterex boasting a skull that could stretch well over 5 feet. Africa's Carcharodontosaurus patrolled floodplains that are now desert, while Morocco's Spinosaurus ruled with a crocodile-like snout and giant, sail-topped back, hinting at a semi-aquatic lifestyle. Every continent became a stage for its own dominant beasts. On island fragments, new names stepped into the spotlight: Abelisaurus in South America, Majungasaurus in Madagascar, Maposaurus, Tarbosaurus, Acrocanthosaurus. The cast was huge and always changing. The rise and fall of these predators was shaped by geography, by continental drift fracturing the ancient world, and by new challenges from every direction. Apex predators didn't just eat, they sculpted entire ecosystems. Their presence pressured herds to move, encouraged herbivores to develop new defenses, and kept every balance of nature in flux. Some ruled for centuries, but none forever. New climates, new seas, tougher competition always meant another challenge on the horizon. When conditions were right, something faster, more specialized, more robust took over. The ultimate bone breaker with a massive head, jaws that could crush, and arms that seemed tiny but deadly. T-Rex was coming, but the world had hosted many giants before its curtain call. The story of dinosaurs has changed dramatically. No longer do we picture them as cold-blooded, scaly sloths, lazily dragging tails through a drab world. Fossils now show skin impressions, delicate patterns, and evidence for nests, eggs, and sometimes unexpected behaviors. The discovery of feathers rewrote the rulebook. Not every dinosaur had them, but enough to shift our imagination. The first feathers weren't fancy, flight-ready plumes. They started as simple tufts, quills, or fuzzy coats, more insulation than wing. For creatures with high metabolisms, warmth was a big advantage, especially for smaller or younger members of the pack. Feathers began as heat trappers but also evolved into tools for display and camouflage. Some fossils still preserve pigment, giving us hints of vibrant stripes, spots, and even iridescent colors. Communication, too, became part of the feather's function, signaling to rivals, attracting mates, or perhaps blending in with surroundings. Eventually, feathers helped with flight, but that was a bonus, not the origin. Parenting also got an upgrade. There's evidence that theropods didn't just lay and leave, they brooded over their nests, limbs tucked, heads low, protecting eggs in ways nearly identical to modern birds. Some fossils even capture embryos inside their eggs, frozen mid-development. These attentive adults likely turned their eggs, kept them warm, and guarded them fiercely, taking risks for the next generation. Instead of mindless, cold-blooded brutes, these creatures invested energy and care, building a legacy far deeper than fossilized bones. That careful, attentive parenting didn't show up in every dinosaur group. Yet, among the theropods, the same lineage that would change the future of animal life, evidence of brooding, communal nesting, and visual display, appears over and over. These dinosaurs often returned year after year to the same places, establishing nesting colonies and tending their eggs. They fluffed feathers, advertised with color and movement, and layered complexity onto the puzzle of their lives. When you start to piece those clues together, something familiar emerges, not an abrupt leap to birds, but a gradual blurring of the line between dinosaur and avian. The transformation wasn't sudden or simple. A branch of small, feathered theropods, first using their plumage for warmth or show, later tested the air with gliding, and finally managed true powered flight. These weren't modern birds yet, but they weren't classic dinosaurs either. Archaeopteryx, discovered over 150 years ago, stands as the poster child of transition. Its fossil story is almost mythical. A creature with both feathered wings and clawed hands, sharp teeth inside a beakless jaw, and a long tail perched between worlds. It could fly and perch in trees, but still bore so many remnants of its reptilian ancestry. It wasn't the first bird nor the last dinosaur, but one beautiful midpoint. Since then, new fossils have pushed the boundary ever further. Microraptor had flight feathers on all four limbs. Caudipteryx sported symmetrical feathers and lightweight bones. Confuciusornis combined a beak with still primitive traits. With each discovery, the origin of flight and bird-like qualities gets traced further back, showing that gliding, soaring, and lift didn't evolve just once. Multiple dinosaur lineages flirted with flight, and plenty of feathered forms never left the ground at all. Not all of these so-called bird dinosaurs were meat-eaters. Some were omnivores or plant-eaters, but still built careful nests and brooded their clutch, draped in feathers for warmth and signaling. Many gathered in flocks, migrated with the seasons, and in some cases developed surprisingly complex social lives. The implications are staggering. The age of dinosaurs didn't truly come to a close with the cataclysm. Even after the asteroid, the story continued. A branch of small, quick, warm-blooded, feathered theropods survived when most others vanished. These outliers had what they needed: small, lightweight bodies to survive the famine, the agility to escape predators, and most critically tools that had already made them successful in their old world. Feathers, sharp senses, high energy, and parental care were their inheritance. Those survivors are still with us. Every robin, eagle, parrot, and penguin is proof. Every chick huddled in a snowy nest, every flamingo standing on one leg, all are direct descendants of those ancient feathered, two-legged survivors. Their arms became wings, their jaws transformed into beaks, and their eggs remain nearly unchanged in design. When you hear birds singing at dawn or watch them build a nest, you're seeing echoes of a story stretching back not just to reptiles, but to the actual dinosaur family tree, one shared with Velociraptor and T-Rex. Birds don't just resemble dinosaurs, they are dinosaurs, and their story is still unwinding across every continent. As dinosaurs were strutting, fighting, and making their mark above ground, a different story was playing out in the shadows. For more than 150 million years, mammals lived in the background, sometimes prey, mostly small, nearly always invisible. Dinosaurs thundered across plains, filled the air with roars and colors, laid claim to swamp and forest alike. Mammals carved out a quieter life. Their ancestors, the synapsids, first split from the shared reptilian family tree in the Permian era, and for a long time ruled the land. After the harsh mass extinction at the end of the Permian, most synapsids disappeared, but a handful persisted. These survivors gave rise to the cynodonts, small, agile, and increasingly strange. The bones in their jaws began shrinking and sliding inward, eventually forming the building blocks of the mammalian middle ear. Their teeth began to specialize: incisors, canines, molars, all emerging with distinct roles. Fur became common, warm-bloodedness crept in, still incomplete, but showing a new way to live. Cynodonts didn't challenge the dinosaurs directly, but instead found new ways to thrive. They shrank, diversified, adapted, and faded into the background as generalists and specialists, eating anything from bugs and plants to eggs and lizard hatchlings. Over untold generations, these animals pioneered a new approach: quiet innovation from below. By the late Triassic, the first real mammals had emerged, furry, shrew-like creatures with extraordinary hearing powered by their newly modified ear bones. Most probably laid eggs. Many nursed their young, huddled in burrows or beneath logs, while dinosaurs stomped overhead. Fossil remains are scarce. Tiny bones don't survive easily over millions of years. But what we do find is remarkable. Some early mammals had long, powerful hind legs for leaping, gliding wings like flying squirrels, and adaptations for burrowing or climbing. Rather than all chasing the same survival plan, they were testing every strategy imaginable. Mammals didn't compete with the dinosaurs for dominance. There was no contest. The top, the middle, the biggest share of every food chain was already taken. Instead, they thrived in the margins, in trees, burrows, nests, or wherever the giants slept. Most led nocturnal lives, a decision that shaped their future forever. Cool nights meant fewer predators and less competition. It also changed their bodies. Mammalian eyes and brains grew better at processing darkness, sound, and smell, leaving echoes still seen in most species today, where keen sense of scent or excellent hearing remains common. For millions of years, mammals stayed small, with only a few lineages ever reaching dog or badger size. Still, they didn't stagnate. Placentas evolved, many mammals developed live birth independently, not just monotremes laying eggs, but advanced forms carrying young within. Reproduction became a new game. Fewer babies, more care, more learning per offspring. Their teeth sharpened, claws grew precise, brains expanded, and behaviors got more complex. Parental care, social bonds, even learning by observation. They didn't wait passively. They adapted and diversified in every direction the dinosaurs left open. Then, when disaster struck, mammals were ready. As the age of giants ended, the small and adaptable saw their opportunity. While dinosaurs still ruled above, they watched quietly from tunnels, trees, and leaf piles, every sense alert for signs of danger in a world that was about to change. And then the sky changed forever. It might have started as a streak of light, maybe hidden by clouds, maybe blazing from horizon to horizon. What followed rewrote the world in seconds. Light, then overwhelming heat, and a sound no ear had heard before. The Earth itself didn't just witness impact, it was scarred by it. 66 million years ago, a rock the size of a city slammed into what's now the Yucatan Peninsula. That single collision ripped a crater over 150 kilometers wide and drilled 20 kilometers deep. It unleashed more energy than any bomb, more than all of human history could generate, a single instant that marked the true end of the dinosaur age.